Oh, there we go.
Yeah.
Okay. Christy did it for us. Thanks. Great. Well, thanks for joining us this evening for our presentation titled Low-Cost Heat Pumps Can Reduce Natural Gas for Space Heating. This is one of a series of presentations organized by the Climate Change Group. I'm Andreas Musing. I'm the organizer for today's presentation. Just a bit of background. Back in 2020, in an effort to reduce my personal carbon footprint, I decided to replace my 20-year-old air conditioner with a low-cost heat pump. The results were actually beyond my expectations. A year later, I was approached by our guest speaker, Erik Janssen of the Sustainable Technologies Evaluation Program at the Toronto Region Conservation Authority. Erik was developing some case studies to show how effective a low-cost heat pump can be in our area. Erik developed a few case studies based on our home and a few other homes in the area. So I invited Erik to join us tonight to share his insights with us. So I'm really looking forward to his presentation. Note that we will be using a website called Slido for posting questions. We'll be putting a link to it in the chat window shortly, and we'll have a few reminders throughout. So if you have any questions for Erik, please post them at that website. And at the end of the presentation, we'll ask some of the questions for Erik to answer. So let's get started. I'd like to now introduce Christy Guo to say a few words. Christy.
Thanks, Andrews. Hello, everyone. Good evening. I'm Christy Guo, the organizer of today's seminar. I'm so excited to have you here and learn, share, and discuss the climate change challenges, potential solutions, and adaptation mitigation. I would like to start my introduction for the seminar by acknowledging that we are meeting on Aboriginal land that has been inhabited by Indigenous people from the beginning. I want to show my respect for their contributions and recognize the role of treaty making what is now Ontario. Hundreds of years after first treaties were signed, they are still relevant today. We are grateful for the opportunity to meet here, and we thank all the generations of people who have taken care of this land for thousands of years. Climate change is becoming a significant topic that we cannot avoid and should take actions as soon as possible. This seminar is organized under a group of people at the PEO who care about climate change issues and really want to make a difference based on our multidisciplinary background. Our mission is to help engineers, practitioners, academics, decision makers, and regulatory committee members to set a vision and work on action plans, strategies for climate change adaptation and mitigation. I would like to express my appreciation for all our co-sponsors who have been working so hard to make this event happen. Without your support and collaboration, we cannot go so far. Now, please welcome our co-sponsor representatives and members from PEO Toronto-Humber chapter, who is the lead chapter, PEO York chapter, PEO Ottawa chapter, PEO East Toronto chapter, PEO Peterborough chapter, Institution of Electrical and Electronics Engineer, Peterborough chapter, Toastmasters Speaker Club of Ryerson Engineering, Toastmasters Toronto Engineering Club of Speakers. Now, I will pass my torch to Amanda to introduce our guest speaker, Erik Janssen.
Thank you, Christy. Tonight, I have the pleasure of introducing our speaker, Erik Janssen. Erik Janssen is a data analyst specializing in energy and has a background in physics and engineering. Since 2013, Erik has worked in the Sustainable Technologies Evaluation Program, STEP, for the Toronto and Region Conservation Authority. He is the scientific lead for the pilot program evaluating the performance on emerging low-carbon technologies with a focus on photovoltaics and heat pumps. Previously, Erik has worked at Ecologix Heating Technologies, a small-scale manufacturer of ground source heat pumps and cold climate air source heat pumps. Erik has an extensive background in physics and engineering. He is a certified measurement and verification professional with the Association of Energy Engineering. He has a Master's of Applied Science in Engineering Physics from McMaster University, a Magisterexamen from the Swedish University Dalarna in Solar Energy Engineering, and a Bachelor's of Science in Physics from Brock University. Without further ado, here's tonight's speaker, Erik Janssen.
Thank you, Amanda. Let me just get my slide up here. Thumbs up if we can Okay, perfect. Okay, thank you, Amanda, and thanks to the PEO Climate Change Group for having me here today. My name is Erik Janssen. I'm an analyst with the Toronto and Region Conservation Authority, and I was invited here today by Andreas to talk about low-cost air source heat pump options, and we're looking at single-family homes today. So let's get started. First, a quick introduction to my organization. As I said, I'm from the STEP program. We're a not-for-profit collaborative research initiative within the Toronto Region Conservation Authority, or TRCA. We do research that supports the uptake of different emerging low-carbon technologies in different fields, buildings, renewable energy, and smart grid as well. A typical project for us would be to take a kind of a promising new piece of equipment, put it in an actual building or in our lab, which I'm showing here, which is in Vaughan, Ontario, install some sensors and data monitoring, measure how well it performs, get an understanding of the business case and other qualitative factors, and then report on the effectiveness of it in different forums like this today. To do this work, we collaborate with different organizations, including government, NGOs, academia, and industry. Essentially, what we do is just try and study these sustainable solutions at a local level, understand how well they work, and then disseminate those findings to individuals and decision makers to help make informed decisions and help move the needle on climate change and drive us towards a more sustainable society. The research that we do gets presented in different formats and forums, but for the most part, all of the work that we do gets is made available freely on our webpage, sustainabletechnologies.ca, in these short, relatively accessible white paper formats. And a lot of the case studies and research that I'll be talking about today is available online for further reading if that's of interest. Quick introduction to myself as well. I've been an analyst with the STEP team for about 10 years now. I'm the scientist on the team leading the pilot projects that we do, for my part focusing mostly on heat pumps and renewable energy systems. I'm a CMVP with the Association of Energy Engineers. Essentially, that means I just know the math to be able to calculate the energy savings from energy conservation measures or retrofits. I did spend some time prior to STEP working for an air source heat pump manufacturer, and my background is in sciences and physics and engineering physics. I'm not myself a professional engineer, nor am I a mechanical engineer. I don't design or install these systems, so I have no services to sell you or products to sell you. I'm sort of a disinterested third party here. You can think of me as a data scientist that's specializing in the measurement and verification of these heat pump systems and other renewable energy systems as well. A quick overview of the talk today. I'm going to talk about carbon emissions. Mostly the context I'm coming from is the Greater Toronto and Hamilton area, so I have some slides on that. But this also applies to many municipalities throughout Ontario as well. We'll talk about carbon emissions in that context. Then we'll go over a quick introduction to heat pumps. We'll talk about the different types of air source heat pumps that are available, as well as some historical barriers and how that's now beginning to change with new policies and programs. Then we'll get into some actual physical examples of heat pump retrofits. We'll start off with an example of a cold climate air source heat pump, and then go on to hybrid heating, which will be the brunt of the talk, maybe about the final half to 1/3 of the talk. And if you've heard me speak on this before, we did kind of give this link out publicly. There's going to be some new analysis in the presentation today, so I do encourage you to stick around, even if you recognize some of the opening slides. So we're here talking about, I mean, many municipalities and Canada as a whole has recognized there's a climate emergency. We need to reduce our carbon emissions and we need to reduce them quickly. The City of Toronto, for example, has targeted net zero carbon emissions by 2040. Canada has set a goal of 2050. And this is really a monumental change of where we're at today. It helps to understand where our carbon emissions are coming from. And in the Greater Toronto and Hamilton area, the Atmospheric Fund does an annual inventory of where our emissions come from. And buildings are really the major culprit, and that's followed by transportation and then heavy industry and agriculture and other sectors. So if we want to reduce emissions, one of the key places to look is buildings, and we really need the urgent energy upgrades of nearly every home and building to be able to achieve our climate targets. We can look at how, we're going to talk about homes today, so we can look at how energy is used in homes. So this applies to all of Canada. This is from Natural Resources Canada, but it works for Ontario as well. Not surprisingly, most of the energy we use in our homes is for space heating. It's a cold climate. And then that's followed up by water heating, and then appliances and other end uses as well. And the large majority of the heating in Ontario is done with carbon-intensive natural gas. So if we want to reduce carbon emissions as a society, we need to look at buildings. And if we're looking at buildings and homes, we need to look at that natural gas that's used for space heating and water heating. And of course, any solution that's going to really make an impact is also going to have to be cost effective for homeowners as well. So this is an important criteria we need to talk about. And that's why we're interested in heat pumps, because they're offering a lower carbon alternative to conventional heating systems. We're talking about reducing the carbon emissions in homes. There's different approaches to doing it, and they're not mutually exclusive. They can all be used together. There's the building envelope, so reducing air leakages and the warm air that might just leak out through the building envelope, through cracks and doors and windows and through the attic. There's the actual kind of thermal R value of the building envelope itself, the level of insulation that's there, and the heat that gets lost through the windows. Then there's the mechanical system. It's possible to upgrade your furnace or boiler to a higher efficiency air source heat pump or ground source heat pump, for example. It's possible to use renewable energy and also power your mechanical system by a cleaner fuel in the form of electricity as opposed to natural gas. And thirdly, there's also, I guess you could say, behavioral and control approaches. You always have the opportunity of using less hot water, taking shorter showers, reducing the thermostat set point. I think this is part of the solution, but it's not the thing that is going to get us to the net zero deep carbon emission goals that we're looking for. On this topic, I think the low-hanging fruit, if you talk to energy advisors or other folks in this field, the low-hanging fruit stuff is pretty much always recommended in terms of the envelope upgrades. If you have a leaky building envelope, air sealing is particularly impactful at reducing the energy usage. If your insulation in your attic isn't up to snuff, that's a relatively low cost and easy thing to do that can really improve the energy usage of your home. And if your windows are approaching end of life, of course, it makes sense to upgrade those to a higher efficiency option, because the windows are sort of the weak link in terms of heat loss in the building envelope. So this is all stuff that we need to consider. But if we're talking about truly deep carbon savings and deep gas savings in buildings, we need to start thinking about building energy standards like the Passive House Standard for retrofit, which is called the EnerPHit standard. It's going to reduce the emissions or the energy consumption of existing homes by 75% or more. This is a really great standard to be aware of. It's an excellent idea. It's encouraged whenever there's budget to do it, but the cost to do that kind of invasive retrofit is often a barrier. And for that reason, we don't really see the mainstream uptake as that is a solution, despite the fact that it's still an important part of the overall puzzle. So that is why we're interested in heat pumps. They're going to reduce the carbon emissions of a home ultimately through two pathways. One, you're switching from a high carbon fuel in the form of natural gas to a lower carbon fuel in the form of electricity. And there's a caveat to that. In Ontario, the situation may be changing, and we'll talk about that on a later slide. And then lastly, there's the drastically increased heating efficiency versus conventional options. So let's explore an example. Here's your home. It's sitting outside in relatively cold temperatures. And because of that temperature differential, it's always going to be losing heat to the outdoors. This is just for the engineers, this is just the heat transfer equation. Heat travels from hot to cold. The normal solution to this is to use a natural gas furnace. So we take the chemical energy that's contained in natural gas, we burn it. That burning releases all that energy, and that heat then gets delivered to the home at the same rate that heat's being lost from the home, and we're emitting carbon emissions in the process. An important point here is that because of the conservation of energy, another kind of physics principle, you're never going to get more heating energy out of that furnace that was there in the gas to begin with. So there's this 100% efficiency limit, and practically we see maybe furnaces approaching 95, 96% efficiency. A heat pump is really a fundamentally different way of heating your home. you're going to be consuming a smaller amount of energy, typically in the form of electricity. And rather than just releasing the energy that was contained in a fuel, you're going to be taking heat energy from somewhere where you don't want it, which is the cold outside air, and then pumping it to your home. So because we're not releasing the energy that's in a fuel, we're not limited by this 100% efficiency limit of conventional gas heating equipment. In fact, a heat pump is able to deliver 3 times more heating energy than it takes to power the cycle, than the electricity that gets consumed. So even a low efficiency heat pump is much more efficient than every high efficiency gas appliance, because we're moving heat rather than just releasing the heat that's in the fuel. And heat pumps also provide cooling as well. Now, for this reason, I think a lot of the folks in the industry think heat pump is a bit of an unfortunate name, because it doesn't underlie the fact that it's both a heating and a cooling system. But for the engineers in the audience, I think a heat pump is really the perfect name. What it's doing is pushing heat energy against the gradient in which it normally wants to flow. Heat wants to go from hot to cold. A heat pump can make it flow from cold to hot. It's exactly analogous to a water pump. Water wants to flow down a hill. If you invest a bit of energy in a water pump, you can pump it back up the hill against the direction it wants to go. So it's the same basic concept. So this sounds kind of like magic to those uninitiated to heat pumps, but it's really just refrigeration, a technology that we use every day. And I think the first point here, kind of the immediate objection is, wait a minute, how can you get heat energy from cold outdoor air? The first thing I would say to that cold is a relative term. Cold to me isn't the same as cold to a polar bear. The coldest temperature you can get is minus 273 Celsius. And provided we're above that temperature, there's useful heat energy that's in the air. So even air that's at minus 20, it seems cold, but there's still a lot of heat energy in that air that can be extracted and used to heat your home. So going back to this fridge analogy, you can think about what a fridge does. It doesn't add cooling. What it does is remove the heat energy from the fridge, but that heat energy has to go somewhere. And it ends up getting pumped to the back of the fridge, and ultimately ends up heating the room, your kitchen, where the fridge is installed. And this is exactly the same process that's happening with an air source heat pump. We're taking heat from somewhere that's cold, which is the inside of the fridge or the outdoor air, and we're pumping it to somewhere else. The thing is that we get more heat energy out of this process than we invested to begin with, so we get a higher efficiency. And one of the magic things about modern cold climate air source heat pumps is that this works even in extreme cold conditions. So there's a variety of heat pump options for your home. There's heat pump options for your hot water. There's geothermal or ground source heat pumps, which is another very important technology for the transition to low carbon. But I was invited today to talk mostly about air source heat pumps. So that's what we're going to limit the scope of the conversation to today. This is a quick schematic of what an air source heat pump looks like. It's essentially, it's an air conditioner that can operate in 2 directions. It looks the same as an air conditioner. It has many of the same components in terms of the refrigeration components. It's typically a split refrigerant circuit. So we have something on the outdoors of the house that looks like an air conditioner, and something on the indoors, which could be a ductless fan coil, an air handler, or even integrated into a furnace. Then we have some refrigerant piping that's connecting the whole system together. And we have some components, that compressor expansion device that should be kind of familiar to HVAC folks as just being the standard stuff for an air conditioner. So it's nothing terribly new. There's many different types of air source heat pumps. I'm going to go over them quickly here today. We don't need to remember all the categories. I think the major takeaway for today's audience is that a heat pump isn't a single kind of metal box. There's many different types of heat pumps, and there's heat pumps that are available for all the different applications and types of buildings that are out there and types of homes. For example, there's ductless mini splits. We have a single outdoor condenser connected to a single indoor ductless fan coil. I think most of us have probably seen that before. Scaling that technology up a little bit, we have ductless multi-splits. So we have one outdoor condenser that's connected to multiple ductless indoor fan coils. You can run the refrigerant lines on the exterior of the building. So this picture is actually from a pilot of this technology that we did back in 2018. This is especially beneficial for electrically heated homes that don't have any heat distribution systems, that doesn't have ductwork or any hydronic piping for a boiler. So you could essentially easily retrofit a heating distribution within a home using that approach. There's ducted mini splits, another way of kind of retrofitting a heating distribution systems. I don't think that one's so common in our climate. At least I haven't seen many examples of that. There's also monoblock heat pumps. So all the refrigeration components are contained in one unit that's kept on the inside of the home or apartment unit. Then air is ducted in and out. Less common for homes, but very relevant for a multi-unit residential sector. And these are pictures from an installation that I actually did in my brother's backyard. He had a small garden suite office, and I got my dainty analyst hands dirty a little and installed a heat pump myself. And that's been working well for him so far. So then moving on, there's also centrally ducted air source heat pump options. So looks very similar to a furnace, except it's an air handler. In this picture on the left here, it's mounted horizontally. But again, it's a big metal box, kind of looks like a furnace, connects to central ductwork, just like a furnace would. There's air to water options. Could potentially be a replacement for a boiler, but there are some considerations around that we're not going to have time to get into today. And lastly, there's hybrid options. We have something on the outside of the building that looks like an air conditioner. It's actually an air source heat pump, and it actually works in conjunction with a furnace. And we're going to talk about this quite a bit in today's talk. It's muted temporarily there. That's my whirlwind introduction to kind of the physics of heat pumps. So why don't we see more of them if they're so great? I think there's different barriers. The two main ones historically have been they cost more than conventional equipment to buy and also cost more to operate. And for that reason, we don't really see many of them today. But that's starting to change. Upfront costs are being reduced. We see no interest loans being proposed at the federal level from the CMHC, at the municipal level. This is kind of on the horizon from the City of Toronto. There's rebates that are now available for some heat pumps federally through the Greener Homes Grant. We're learning more about low-cost options like hybrid systems. There's different ownership structures that are being explored. There's a leasing ownership structure being explored for geothermal right now. We might see that same thing come to air source heat pumps as well. On the operating cost front, we have carbon pricing, which is increasing the cost of natural gas faster than increases in any rates of electricity. There's new rate structures that are being announced for electricity that are especially beneficial to air source heat pump, and we'll see an example of that soon. The equipment efficiencies are higher than ever, and that's also promoting lower operational costs. And lastly, I think a holistic financial analysis based on net present value rather than something kind of like simple payback is also really helpful to truly understand the total business case for the technology, and we'll see an example of that as well. So now I just want to go over a few key policies that are in development now that are going to help air source heat pumps. So I mentioned the federal Greener Homes Grant. Right now, they're offering up to $5,000 for larger high performance air source heat pumps. So that's a really important development. I mentioned we also see 0% interest loans being proposed, not available yet, but it has been announced by both the CMHC and the City of Toronto that it should be coming soon. 0% interest loans are especially interesting. They ultimately do two things. Firstly, of course, they spread the cost out over the system lifetime. So we don't have this one lump sum payment, which is just nicer. So we're talking about kind of a monthly payment that's really going to be a smaller net payment because if we install our heat pump, we're going to get some monthly savings. We have some cost to pay, but then we're talking about a small net cost that has to be paid every month, and that's just more manageable than one large upfront cost. And then because it's able to defer the cost of the heat pump to future years at no penalty, it effectively makes the heat pump just cheaper. And this should be familiar with those that are used to doing financial calculations, but money has a time value. Cash flows in the future are worth less than cash flows that happen today. And I think we intuitively understand this. If I were to say you can pay $1,000 today or $1,000 in 5 years, you'd probably choose the 5 years because you know, well, I can invest that $5,000, get a return on my investment, and I'll be better off in the future with, I'll have more money. So we can express future cash flows in today's dollars using some financial calculations and some assumptions around what's called the discount rate. It's just a parameter that we use to express future cash flows in today's dollars. If we were to do an example to look at, okay, what's the difference between paying $1,000 today versus paying $1,000 in even payments at no interest over 15 years? What does all that mean to me in today's dollars? We can do that calculation and assume different things about the discount rate, but with these assumptions, it's about 30% cheaper. So because there's effectively giving away money at no interest, it makes the equipment cheaper, and this is really important. We can also take a look at carbon pricing. So we can look at the cost for delivering heat for different home heating options. It's a pretty straightforward equation. It depends on the utility rate and also the efficiency of the equipment. These are the most current rate. There was recently a large bump in natural gas. Natural gas has some volatility, so it can go up and down, but this is the most recent rate. It's delivering heat. It can deliver heat to your home at 4.7 cents per thermal kilowatt hour, and that would be for a high efficiency 95% natural gas furnace. Now, you're probably used to kilowatt hours in terms of electricity, but kilowatt hour is just really, it's a unit of energy. It could be heat energy or electrical energy. If we're talking about heat pumps, it's sometimes easier to refer to thermal kilowatt hours. We can look at the cost of a high efficiency air source heat pump at current electricity rates. And again, taking into account utility rate and the efficiency of the equipment, it's already going to be lower than a furnace. And if we look at a low efficiency heat pump, it's going to be a little bit more, but not that much. So already at current utility rates, we can expect close to comparable or even better operating costs if we're going to use a heat pump instead of a natural gas furnace. And this situation is only, this gap is going to widen in the future. The federal government has a pricing schedule for the price on carbon. It's going to be $170 per ton by 2030. So there's quite an increase still that's going to happen on an annual basis for the cost of natural gas, meaning that that's going to benefit kind of heat pumps more and more moving forward into the future. This was just announced as well. They're considering or proposed a new ultra-low nighttime rate structure for electricity. This is, of course, going to be incredibly beneficial for electric vehicle drivers. At 2.5 cents per kilowatt hour is really dirt cheap. But this is a large benefit to heat pumps as well, especially ones that have kind of smart switching technology that can prioritize operation during low cost time of use brackets. And we'll see some calculations around that as well. So those are just some recent policies to keep in mind, all of which is helping to drive a strong business case for air source heat pumps. Okay, so let's jump into a specific example from some of the work that we've done. We worked with this homeowner. She's the owner of a Victorian townhome in the city of Toronto. She installed a high performance cold climate air source heat pump, fully electric, completely replaced her furnace and AC system. It connects to the central ductwork of the home. So we have this air handler on the inside of the home that replaces the furnace, and outside we have a fan coil that sort of looks like it would with a large air conditioning system. Again, use the existing ductwork, so not a lot of extra effort was required there. It did require her to have an electrical service upgrade to her home as well. I should mention that. She has a cold climate version, and that's just kind of almost a slang term to mean that it can continue to function in really extreme cold conditions. The latest equipment from Mitsubishi and from Daikin and other manufacturers is operating down to -30 Celsius. It's not terribly efficient at that temperature, but it is still continuing to pump heat above a COP of 1 at really cold temperatures. The unit's also variable capacity. That means it's essentially always on. It's just modulating its heating output to the heating requirements of the home. It's beneficial for a few reasons. It's more efficient. It's also more comfortable and a little bit less wear and tear on the equipment because it's not kind of banging on and off at full capacity. This retrofit also uses a backup electric resistance heating coil, which is pretty common with these retrofit. It's just a small add-on to the system. It's essentially a little bit of redundancy. For that rare, extremely cold day, it's just a way of making sure that there is enough heating capacity to maintain the thermostat set points of the home. So this homeowner was kind enough to share her utility bills with us pre and post retrofit for a full heating season. She also shared all of her installation invoices, so we got all the insights into the cost data for the equipment. We did our own little analysis. We looked at the utility savings and then also projected in the future as to where this might go as a result of carbon pricing. What we found was her net utility cost at current rates, or at least at the rate at the time we did the analysis, was already like slightly lower or on par with just conventional natural gas furnace. And that was going to increase moving out to 2030 as carbon pricing really ramped up. The rates have since increased since we last did this, from 40 cents per meter cube to 47 cents. And updating that, we get a slight bump again in the cost savings that we're going to get from the system. At the same time, the carbon emissions from her home was drastically reduced, or the carbon emissions, I should say, for her space heating. We also used her. So one of the issue, not issues, but one of the things to note about these high performance central cold climate air source heat pump systems is that the upfront costs, I mean, there's no getting around it. It's much higher than just your kind of basic furnace and AC system. So if you were to kind of just look at the upfront costs, maybe some people, you might lose some people just at that point right there. One of the things we wanted to do was let's do a holistic financial analysis. Let's calculate the net present value, taking into account all sources of costs and savings, and trying to understand the full life cycle costs, again, putting it in the context of today's dollars. So there's various costs. This was a bit of a theoretical exercise. She did this retrofit before rebates were available, also before no interest financing was available. It's not available yet, but like theoretically moving forward, what does this look like for a future system owner? So of course, high upfront costs, but if we apply no interest loans and we apply a $5,000 rebate, that upfront cost comes down drastically. Electrifying her home, her full home, getting off natural gas entirely, would also require her to replace her electric water heater and her stove. And this is going to vary with home to home, but that has a cost associated with it too. In her case, we kind of theoretically said, well, let's just assume an electric resistance water heater. It's a single occupant. She has a very low water heating load. So for her case, that made sense. For other homes, a heat pump water heater might make more sense. So that's the cost. We can total all that and put it in today's dollars. Then there's sources of savings. So by installing the heat pump, she's avoiding the cost of furnace AC. She's avoiding the cost of having to replace her stove and condensing on-demand water heater in the future. She's got lifetime utility savings. We saw that on the last slide. Some property insurers will give you an insurance reduction if you heat with electricity instead of natural gas. Not all of them, but it's worth checking. We've included that cost. It's small, but just to, again, holistic financial analysis. And one of the largest sources of savings is actually the cost of not having to maintain an account with the gas utility. You pay $25 a month or $300 a year just to it's a fixed cost regardless of how much gas you consume, just to maintain an account. So if we can assume that's going to be constant moving forward, and we don't know exactly, but for now we can assume that's a large source of savings as well. So we can total up all our costs, total up all our savings, and what we get is full electrification, at least for some homes. It's not a gigantic difference in cost, and it's much smaller than that initial upfront cost would have you believe. And if that cost is actually spread out over the system lifetime. So if we talk about what does that mean on average in terms of dollars per month, one of our calculations, again, depends on what you assume, maybe on the scale of about $10 a month. So for the cost of a Netflix subscription, at least in some homes, it might be possible to fully electrify. So takeaways in the context of rebates, no interest loans, and carbon pricing. So these three key policies, full electrification of homes, getting off natural gas entirely, can approach cost effectiveness with just business as usual. Lots of caveats to this, I would say, in some homes. The variation from home to home is going to be very large, and there needs to be a case-by-case analysis. Property insurance reductions might not be available from every insurer. Some homes are going to have a lot of gas loads, the stove, the dryer, fireplace, and barbecue, and that, of course, is going to add cost to fully electrifying. Performance is going to be different in different homes. And ultimately, we can assume what's going to happen over the next 15 years, but I don't have a crystal ball and the future is going to be uncertain. All we can do is assume scenarios, state our assumptions, and then calculate the results. Ultimately, I think the takeaway here is that there's a different framework in which we should look at fully electrifying homes. And the bottom line is just not stop at the high upfront cost, to dig a little deeper and try and understand the full life cycle costs. And that might help to persuade some people who are already considering it to take the step and fully electrify. So the full details about that analysis are available online in a case study document that's on our website. We can also talk about the homeowner experience, which is an important piece of the puzzle, again, documented in the case study. Overall, the homeowner was very satisfied after going through a full heating season with it. The heating's constant. The noise level is less inside the home than with the gas furnace. And the anxiety on the running cost was totally abated once she ended up going through a full heating season with it. Okay, so that is cold climate, all electric, complete electrification of a home. That's a case study that we've done in the Toronto context. Now let's talk about hybrid heating, and this is what we're going to talk about for the remainder of the discussion today. So a hybrid heating system, it's an air source heat pump system that utilizes both a furnace and an air source heat pump. You can think of it as the air source heat pump effectively just replaces the air conditioner, or even maybe a better way is that it's an upgrade to an air conditioner. You can use it with an existing furnace. So this is really important. There's a lot of folks out there that have a newer furnace and may have an AC that's getting older. Well, it's possible to use the air source heat pump with an existing furnace. The main benefit to the hybrid approach is ultimately that it can just have much lower upfront costs than fully electric options. And this is ultimately for two reasons. Typically, if we're not going to require the air source heat pump in extreme cold, it can be just smaller and it can be simpler, because we don't need all the bells and whistles that are associated with some of these high efficiency premium models. So smaller and simpler heat pumps are also cheaper heat pumps, cheaper from a cost perspective. But an important thing to note is that if we look at the heating load, and again, this data is for Toronto, but it would apply to much of Southern Ontario, the amount of heat energy that our home requires on an annual basis, a lot of it is actually required in relatively mild conditions. So if we want to develop deep carbon savings for our home, we don't need necessarily, we don't have to have a large fully electric air source heat pump. It'll drive deeper gas savings, but we can still get quite a large percentage of our annual gas savings, even with a relatively small and simple air source heat pump. That's much lower upfront cost. There's different approaches to controlling a hybrid heating system. We're going to discuss two. The first doesn't have an official name, but I'm just going to call it the simple control approach. Effectively, you select an outdoor temperature. Above that outdoor temperature, the air source heat pump operates, and below it, the furnace operates, and they never operate at the same time. An important thing to note about air source heat pumps is that they're going to typically lose capacity and efficiency as it gets colder outside, because it gets harder to pump heat. It's, again, using our water pump analogy, if we're trying to pump water up a taller hill with the same pump, typically we'll get a lower flow. Well, in the case of air source heat pumps, the hill is the temperature difference between the outside and inside, and that's called the lift. And the greater that temperature difference, the lower the heat transfer is going to be. At the same time, our building heating requirements are going to be increasing as it gets colder outside. And this should be pretty straightforward. At some point, the amount of heat that the heat pump can supply and the amount of heat that our home needs, those two curves are going to intersect. And that intersection is really the lowest possible switchover temperature that we could get for a home. Because below that temperature, the heat pump it's below the building load and doesn't have enough heating capacity. But you can see that we can drive deeper switchover temperatures through two pathways. One, lowering the building load, maybe through building envelope upgrades that I mentioned earlier, or two, increasing the heat pump capacity. Both those things are going to shift that intersection to colder temperatures and allow us to do more of the annual heating load with our air source heat pump. We can do some calculations around, okay, what is the impact of that switchover temperature on the annual gas savings? We can just assume temperature data from the past 5 years as an example, because of course, This past winter was extremely cold. It was an outlier, and we've had winters before that have, since the winter hasn't come. So it can vary, so it's useful to look at the results of different years. This is some of our analysis at -5. If we can switch to air source heat pump above that value, based on previous year's data, we're in 65 to 80% gas reduction. If we can get down to -10, we're in the realm of 80 to 95%. So if we can get a switch over temperature between -5 and -10, we're really doing the lion's share of the heating of the home with a relatively lower cost air source heat pump. So I would say bigger is better if gas reductions is what we're after, but there's some constraints on the sizing that's gonna vary. Firstly, there's the cost. Bigger is more expensive. Everyone's gonna have a budget, so you're gonna have to pick an option that's within your budget. Two, the existing ductwork might place a constraint on the heat pump sizing. Heat pumps tend to require more airflow. They operate at lower temperatures to deliver the same amount of heat as a furnace. You need more airflow. And this is something that can be looked at by an installing contractor. And three, there might be some constraints around how it operates in cooling mode. In the cooling season, heat pumps are also going to be dehumidifying. If we have a large single stage air source heat pump, it's going to have shorter cycles. It's going to do less dehumidification. And there's some concerns around that. But this can all be discussed with an installing contractor. And ultimately, I would encourage you, if carbon savings are the goal, to select a heat pump that's as large as the home will allow and as large as the budget will allow, because that's what's going to drive the deepest carbon savings. So we've done, like the cold climate air source heat pump, we've done 3 case studies, again, taking actual pre and post retrofit utility data, doing savings calculations, trying to understand carbon savings, and also gathering the homeowner's experience. And Andreas was nice enough to volunteer his home for this work as well. The installed costs of these systems, so both the furnace and the air source heat pump, so they were both new furnace, new air source heat pump, for these 3 systems was $8,000 to $10,000. So we're not talking about gigantic increases over just furnace and AC. It can get higher than that with kind of higher performance or larger hybrid systems as well, and also depending on who installs it. But lower cost options are available. In Andreas's case, he'll be the first to tell you, it was on the scale of about $1,000 more than conventional furnace AC. It can be higher than that as well if we get a higher performance air source heat pump, but again, there's a range. From looking at the change in gas, we saw gas reduction on the scale of 50 to 75%. In terms of utility bill changes, we think it's going to be cheaper either today or in the very near future due to carbon pricing. So utility bills aren't skyrocketing. Homeowners overall across these 3 case studies were satisfied. It's a relatively small sample size, but it's certainly useful takeaways from that as well. And overall, we can look at these hybrid systems. It's achieving very deep gas savings for very low upfront costs. And if you've been around this sector, there's really no other option available where you can spend as low as an extra $1,000 and reduce your home gas consumption by this level. So it's kind of an important piece of the overall puzzle that this is something that can be done cheaply, but is yet very, very impactful. And also, of course, it's an ideal option for homeowners that have a newer furnace and an AC that's approaching end of life. It does make sense to consider the upgrade to an air source heat pump rather than just installing an air conditioner. So we can look at the annual net utility change from one of the examples. So this is Andreas's house. He was a relatively larger air source heat pump at 2.5 tons, and also a low efficiency one on the scale of heat pump options that are available. But with that lower efficiency came a lower upfront cost. His was able to switch over at -6 Celsius, so he did get deep gas savings. We estimated about 74% reduction, which is what we'd expect from some of the theoretical calculations that we can also do. Again, low incremental cost over AC. We found for his unit, his utility rates did increase slightly at the time of the rates at the time where we did the analysis. If we were to repeat that today, we would actually expect a small savings rather than a small increase, and subsequently a larger increase moving out to 2030. But again, he may be having this system for the next 20 years. I think the average furnace lifetime is 18 years, and an AC or air source heat pump would be 15 years. So the savings is going to continue, I imagine, as we continue to try to phase out natural gas through carbon pricing. So again, we have a low cost, low upfront costs, manageable operating costs, and cheaper relatively soon, and deep carbon savings. Homeowner experience from these 3 case studies was also quite positive. Just pulling some quotes, happy with the work done by the contractors and some improvement in thermal comfort, because the heat pump is actually it ends up operating for longer periods of time, so you don't get this kind of blast of heat from the furnace, then it turns off. Second quote there, happy with the slight overall savings in the utility bills. And also there's a comment there about noise, which it does sound like an air conditioner outside. It's a manageable amount of noise inside, and for the homeowner, this wasn't an issue. Okay, so that's the simple controls. Now let's get a little bit more technological and talk about the smart controls. Say that our goal was to create the absolute lowest cost of operation for our heating systems, because a lot of people will primarily be motivated by the financials of it. There's ultimately 2 things that are going to impact the cost of operation for an air source heat pump, and we saw this equation earlier. There's the utility rate, and in Ontario, we have time of use rates. That's going to change throughout the course of a day. And then there's also the efficiency of the heat pump. And I mentioned that the efficiency is going to go down as it gets colder outside. And each heat pump is also going to have its own kind of manufacturer efficiency curve. Better heat pumps are going to have greater curves and so on and so forth. But the point is that both our electricity rate and our heat pump efficiency is really changing on an hourly basis throughout the course of a day. You could imagine if we had a smart web-enabled controller that was able to look at all of the real-time factors and then just make a control decision, like for this hour, I'm going to operate heat pump because it's cheaper. But for the next hour, I'm going to go with the furnace because that's the cheaper option. This technology is available on the market today. I just want to note too, some of them have an annual subscription fee that can eat into the savings, so that's part of the discussion as well. But the basic technological approach of this kind of smart switching is sound. I just want to quickly acknowledge some of the other groups that are doing work in this area. Natural Resources Canada did some good kind of initial work. Mars did a good report going back kind of 5 years now, called the Future of Home Heating. We've done some partnerships with university researchers that are working in this field. Alan Fung at Ryerson University, and Enbridge is also exploring this topic. We don't have comprehensive field data like I showed for the other system options right now for the smart switching approach, but it is forthcoming. We're working with Enbridge right now. They're doing a pilot in partnership with London Hydro. There's 100 homes in London that have been installed with this smart switching technology, and they're offering up their data for analysis. Enbridge also recently received some funding from the provincial government to do a larger scale hybrid in different municipalities throughout Ontario, 1,000 homes, and that's commencing in 2022. So we will have some field data from this approach relatively soon, but we don't have any just yet. But I believe this audience today, we probably have some lay people, but this audience today is composed mostly of engineers. So we can calculate, we can make a educated guess at what we think the impacts of this smart control is. For data inputs, we need to know the weather. For my example calculations, I've used a colder year for Toronto, so 2018, 2019, trying to be a little bit more conservative. I've assumed a mid-efficiency air source heat pump curve and applied some D rates. I can share these calculations for anyone who's interested as well, some of the details. But assuming a mid-range heat pump, assuming a building load that, like Andreas's, switching over at -6, something that's relatively well matched to the heat pump. And then we can assume different scenarios for the utility rates, both current time of use rates, but also the new proposed ultra-low nighttime rate, and even kind of trying to think about what's going to happen moving forward to 2030 as carbon pricing begins to ramp up. So for a calculation procedure, I mean, it's a lot of calculation, but the basics of it is simple. For each hour in our weather data file, we just look, what's our building load? Does our air source heat pump have enough capacity? Yes or no? If it does, then what's the cost of heating with natural gas versus what's the cost of heating with the heat pump based on the current utility rate and the efficiency of the heat pump? Make a control decision. Okay, for this hour, I'm going to use natural gas, or for this hour, I'm going to use air source heat pump. And based on the heating load and the efficiency of the unit, we can estimate what the utility consumption would be, either of natural gas or of electricity, and then just do some accounting tabulate the total utility costs and consumption over the course of the year, and overall make a comparison. Well, this was the cost if I just used the natural gas furnace, and this would be the cost if I did the hybrid approach with smart switching. And also this is the gas savings. I want to caution here, I've done my own preliminary calculations. I haven't published this anywhere. It's good to be able to have the field data to corroborate the theory. I'm not guaranteeing that what I'm showing on the next slide is what you would get in your retrofit, but this is where I sit, where I think the financials will end up. If we have a smart hybrid heating system, okay, so firstly, the plots. What I'm showing in the plots here is the annual heating load broken down according to the outdoor temperature and also the time of use bracket. So this same kind of normal looking distribution is what we saw on the previous slide in terms of how heating is distributed throughout a year. In each of these plots, the darker colors represents what would be done with the heat pump, and the shaded light colors represents what we would do with the furnace. So you can get an immediate sense visually of what fraction of the annual heating load would be done with the heat pump in the darker colors and what's going to be done with the furnace in the shaded colors. If we use this smart control approach at today's rates, kind of what I'm predicting is a gas reduction of 54% and a cost reduction on the scale of $170 within the confines of the assumptions of the analysis. If we were to just use our simple control, operate it whenever it has enough capacity, so above -6 in this example, we get deeper gas reductions at 76%, but lower cost reductions as we're going to operate it at a peak time of use rate where that electricity is the most expensive. Now, the smart controller, like at least the ones that I've looked at, have a subscription fee that's on the scale of $100. So you can see, like at least in this simple example, we're about breaking even. But that subscription fee is fixed. So if we have larger and larger homes, we'd have greater savings, and the smart control approach would start to make more and more sense. But overall takeaway here is today's rates, we're getting gas reductions, cost reductions, and also again, manageable increases in the upfront cost. We can also do some calculations and estimates around the new proposed rate structure. Again, getting a bit theoretical, I don't know the exact marginal cost of electricity with the new rate structure, but we can make some informed estimates. So here again, using our smart control approach, only operating the air source heat pump when it's the cheaper option. Nighttime rate, again, federal government or the provincial government has said they're considering 2.5 cents per kilowatt hour, and then there's some other charges for regulatory and delivery on top of that. But overall, still much cheaper. We would see a gas reduction of a little bit higher at 56%, but a potentially very deep cost reduction of $293. This is just because that nighttime time of use bracket is a significant fraction of the load, and for that bracket, it's going to be, one, electricity is really cheap, but when you tack on the high efficiency of the heat pump, it's a fraction of the cost of a gas furnace. So this would be much cheaper than just using a gas furnace alone. We can do the same thing with the kind of simple control with a new rate structure, a different calculation iteration, same gas reduction, 76%, but a lower cost reduction because part of the new rate structure is going to be a large increase in the peak time of use. So we're going to be operating it during that time as well, where it's electricity is more costly and it's going to eat into our savings overall. We can get even a little bit more theoretical and okay, what does this mean looking out to 2030? Again, I don't have a crystal ball. I can't tell you what's going to happen for sure. What I can do is assume certain scenarios and then just follow the calculations. So in this case, I'm assuming that natural gas increases from its current rate only at the rate of carbon pricing moving out to 2030. Electricity, I've taken current rates and then applied a 2% increase per year. So that might be a reasonable scenario. Ultimately, the future is uncertain and we can't know what's going to happen for sure. But again, because carbon pricing is going to continue to increase, and because our nighttime time of use rate would be so low, we're seeing this cost differential just get larger and larger. Regardless of whether we use the smart control approach or the simple control approach. Again, I'm not guaranteeing this is going to happen, but I think the bottom line and a general takeaway for today's talk is that in a world where we're trying to transition away from natural gas, where we have carbon pricing, where we have new electricity rate structures, completely depending on natural gas for your home heating for the next 15, 18, 20 years, whatever, is likely going to get very expensive. Than at least incorporating some level of electric heating into your home. And ultimately what we see is there's really air source heat pump options for everybody. If you really want the greenest option, that's going to be the all electric cold climate air source heat pump. And we saw some good reasons why we might go that way. If you really just want the deepest possible utility savings, that might be hybrid heating with smart controls, may be the way for you to go. If we want deep carbon savings, low upfront costs, and don't need the absolute lowest operating costs, then maybe we would look at the hybrid heating approach with simpler conventional controls, but trying to get as deep a switchover temperature as we could. So there's options for really every homeowner. There's also some other kind of expanding the scope of the discussion a bit outside of just your own home. Decarbonizing homes is important, and cold climate air source heat pumps is an important part of that picture. So we do need a much greater penetration of that as an option. But if we do end up with a high penetration of all electric air source heat pumps, we're going to have this other issue in terms of grid management. What happens with an all electric option is that as it gets extremely cold, the efficiency goes down and the building load goes up. And those two things ultimately result in electricity spike. And if we have a lot of homes doing this at the same time, it's going to be more challenging for the grid operators to manage. One of the potential solutions, and there's different approaches, for example, geothermal doesn't have this issue, and neither does hybrid systems. The hybrid system essentially just turns off when it gets extremely cold and it uses natural gas. But because it doesn't get extremely cold very often, we still end up with a much lower usage of natural gas annually over the course of the year. So if we had a higher penetration of both hybrid systems and cold climate air source heat pumps and other options like geothermal and deep envelope retrofits as well, we're going to probably have a healthier electricity grid that can manage a deeper penetration of electrification of home heating. So one of the things the folks in this hybrid heating realm also talk about is the potential for integration with demand side management and conservation programs. If you're familiar with the Peak Saver program from Hydro One, they installed smart switches and thermostats in hundreds of thousands of homes. And on those really hot summer days where the electricity demand was the highest due to the air conditioning loads, the homeowners handed over some control of their thermostat set points over to the utility. So if we were pushing the grid against its limit, the utility could curtail the cooling load a little bit. The homeowner could receive some incentive for participating in the program, and ultimately the grid is easier to manage for the utility. You could see this sort of approach being used with smart, not even necessarily smart, but web-enabled hybrid heating systems. If we have both a gas and electricity option and the ability to hand over some of the control to the utility, we could end up with the utility being able to revert to natural gas if it can't handle the electricity load, and overall might be able to achieve a higher penetration of electrified home heating loads using that kind of approach. Another very important thing that's happening right now that we should all be aware of is for this whole electrification of home heating to produce carbon reductions, we also need clean electricity. The federal government has announced they want net zero electricity across Canada by 2035, which is coming up very soon. But one of the situations in Ontario right now is we're losing nuclear generation capacity. So, I mean, nuclear is another discussion, but it's low carbon. So we're losing the capacity because of the retirement and refurbishment of some of the nuclear reactors. The current planning outlook from the IESO is increased reliance on natural gas generation. So that means the electricity emission factors are, if everything goes according to that forecast, are set to drastically increase. There's still a potential benefit to electrified home heating in that scenario, but it's really greatly diminished. If we want this electrification of buildings to really make an impact, we need clean electricity. Now, this is getting far outside of my area of expertise. This is a recent report that was done by the Clean Air Alliance. Ultimately, I just want to point to the fact that there are other options than kind of large scale dependence on fossil fuels if we want to take it. A large important option there is ultimately just expanding the transmission links with Quebec and the clean hydro that they have. Also included would be expanded renewable generation, and even like smaller factors like expanded vehicle to grid charging infrastructure that can then offer some local storage, which is kind of a very interesting emerging topic as well. Another quick point to make here is that air source heat pumps, they really are a key technology in this decarbonization conversation, and electrification is a key approach. But there's really a number of technologies: air source heat pumps, geothermal, hybrid systems, envelope upgrades, distributed renewable generation and energy storage, thermal grids, new technology maybe that we aren't aware of right now. All of them are important, and we will need all of them, and each will find its own niche as we move forward. I also want to quickly plug some recent work that was done by Natural Resources Canada about some guides for homeowners and contractors about how to size and select air source heat pumps. So this is good reading. You can have your contractor work through it to help size a heat pump for your home. A really good tool and resource that they've developed that's available freely online. And there's more coming from my group on this topic soon. We've developed these kind of initial case studies. We're doing more. We're trying to harmonize all of these learnings from local adopters into guidance documents for homeowners, developing a question and answer portal where you can just get kind of third-party guidance from us and from kind of other experts in the field. And overall, just trying to beat the drum about heat pumps through media and social media campaign, letting people know that there is a greener alternative for home heating. We're always looking for partnerships, communication pathways, and ways to collaborate. So if any of that sparks your interest, feel free to reach out, and then we can get the conversation going. Okay, so let's wrap up this chat here. I might be over time already, and I apologize to the organizers for that. So heat pumps, this is the comprehensive breakdown. Heat pumps are reducing carbon because they're driven by low carbon electricity, at least today. And we'll see how that changes in the future. And they're also much more efficient. Those are the two key things. There's many different types of heat pumps. Regardless of the home you have, there's a heat pump option for you. We looked at central cold climate air source heat pumps. They can completely replace a furnace and AC system and can already generate lower utility bills than if you were to just use your furnace and AC system. These systems do have high upfront costs. There's no getting around that. But a full net present value calculation could show potential cost competitiveness, at least for some homes and in some cases. We looked at hybrid systems. It's an air source heat pump option with lower upfront costs. They can have cheaper utility costs today or in the near future. Different control schemes are possible, depending if you wanted greater carbon savings or greater operating cost savings. And ultimately, looking at we don't know what's going to happen with rate structures, but I think the general point remains that having both a furnace and an air source heat pump doesn't really leave you completely reliant on wherever natural gas goes. And if you have an electric option, then you can benefit from new rate structures that might be emerging in the future. And lastly, a very important point is that heating electrification ultimately has to go hand in hand with a low carbon grid if all of this is going to help us meet our goals of net zero carbon emissions at some point in the future. If we were to just have the even simpler takeaways, I would think the final thoughts are these: completely depending on natural gas for home heating is likely going to get very expensive in a world that's trying to transition away from natural gas. And the decisions you make today about your furnace and about your air conditioner, they might stick around with you for the next even 20 years potentially. So it's important to plan for the future. There's different air source heat pump, low carbon options that are available for your home today, depending on what kind of homeowner you are, whether at the higher performance end of the spectrum or the low cost end of the spectrum, whatever is valuable to you. And just as a general kind of question, why would we still be installing air conditioners when we can see all these benefits at the bare minimum, even a low cost one like this did in his scenario, which it nearly pays for itself without having any kind of subsidy. and is going to allow, in his case, him to take advantage of new rate structures and not just be dependent on wherever the natural gas rate goes. So I think there's a compelling option just to let's start transition to air source heat pumps and forget about choosing air conditioners for our homes. Some more food for thought. I added this slide into the last minute, just some stuff that pops in on my LinkedIn feed. I saw that a recent development in Europe is now trying to get on off natural gas at a quick rate. The Netherlands, as of 2026, is now requiring that all new construction has hybrid heating as a bare minimum, and even replacements of existing fossil fuel systems are also going to require hybrid heating systems. So this is a technology that's gaining momentum globally. And similar programs, well, not similar, but another program has recently been announced in Quebec. I'm not sure of the details of that program, but again, looking at this hybrid approach as a low-cost, high-impact way of transitioning homes and buildings off of fossil fuel heating. Okay, we made it. That's the end of the talk. Thank you everyone for coming here today. I really appreciate your time. This is my contact information. You can email me directly. I encourage you to reach out to me and connect on LinkedIn. We're often kind of promoting new research and different kind of interesting things in the heat pump field. So if you want to stay up to date, you can follow me on LinkedIn. I want to thank all the homeowners that have been kind of courageous and taken the first step on their own without necessarily knowing where it was going to go. I think they've made good decisions, and hope their activities is going to end. I also want to quickly acknowledge the funding partners and contributors to the work. Well, we receive a lot of good funding from the Atmospheric Fund, the City of Toronto, Region of Peel, and York Region, and recently the Impact Fund as well, where we're going to be developing our own small hybrid heating pilot program. And lastly, thank the SNAP program, which is a companion program in the TRCA to us, and Imperial Energy is an equipment installer that helped quite a bit in the preparations of the case study and the review from a contractor's perspective. I do want to note quickly that the context of this presentation don't necessarily represent the policies of any of these supporting agencies. If I mention trade names, vendors, or commercial products, that doesn't constitute an endorsement of those products or services. That's the end of my talk. I think there's going to be some question time at the end, and thanks everyone for attending.
Great.
Thank you very much. Thank you so much for the presentation, Erik. You've covered a lot of fundamentals of the heat pumps and many case studies along with the smart control technologies and some preliminary calculations. I love it. A lot of information to take away from your presentation tonight. We'll take a look at the questions from the audience right now. The top one we're looking at is, can the heat pump alone meet the winter heating requirements without a supplementary heater in the Toronto area? Erik, you're on mute.
So I think we're talking about the electric resistance backup heating there. Yeah, I mean, it all depends on the relative sizing of the building heating load versus the heat pump. If you look at the curve of how frequently extreme cold happens, it's really infrequent. It would make sense to have, you'd save some money by buying a smaller heat pump and just having that electric resistance like as a just in case, rather than spending more money and getting a bigger heat pump and doing the full share. Theoretically, yeah, you could do it without the backup heating. And if you're in a townhouse like me, you have your kind of neighbors buffering you on either side. It's even more realistic in that scenario. But I think generally, in terms of optimizing the costs, it makes sense to size your heat pump to do like nearly all of the load. And for that rare day when it's extremely cold, you do have a little bit of backup that you're next to never actually going to need to use.
Okay, thank you. And the second credit question is, there are heat pump products with thermal energy storage to store energy during off-peak hours and for use during peak times. Any comments?
That hasn't come across my radar. You could see how that could be implemented either with an integrated product or even with just kind of a secondary like energy storage, like your Tesla Powerwall, or even now that we're seeing vehicle to grid charging infrastructure, maybe there's some synergy there. I think storage just in general is important, because what's difficult for the electricity grid to manage is when the electricity kind of profile peaks and goes like this. If that can be buffered at all, which is what that ultra low nighttime rate is ultimately trying to achieve, flattening out the nighttime consumption with the daytime consumption by incentivizing nighttime consumption, it's only going to be more of a benefit to the system. So at the home level, like I'm not sure the economics of the storage. Technically, is it feasible? Yes, I'm sure it is, but it's going to add cost. So that's sort of a calculation someone would have to do for their own home.
That's a very interesting point. I actually came across this product during my master's program at University of New Brunswick. I think a bunch of startup students, they had a company called Stash Energy, and they use a heat pump integrated with the thermal storage. Is that
like a phase change sort of thing, I would think then? If you want to store a lot, you probably need a large amount of phase change material.
I'm not sure. That's why I just thought of that product.
I think I've seen something like that using like ceramic blocks or something.
Like those high thermal property.
But you can see like, so just I say phase change material for anybody in the audience, like it's sort of there's sensible heat storage. So like, let's say if you have a ceramic block and you heat it up, it stays hot. But then there's actually taking a piece of material, like for example, they have phase change drywall, where you have this kind of wax that's impregnated into drywall, and it has a phase change temperature around room temperature. There's a lot more energy stored if we convert like a solid to a liquid, then it's just like a sensible change of temperature. So you can totally see how someone might have some sort of phase change energy solution. It's starting to move away from the simple, and I guess with the hybrid approach, especially if we're talking about like in Andreas's case, like kind of simple single stage. The install is more or less exactly the same as an air conditioner. It's like, it's just, I don't know, it's simple, it's easy. It's something that really has legs in terms of a technology that you could see achieving widespread adoption. But the innovation, as you say, is great to see, because we don't know what the future is going to look like in 5, 10, 15, 20 years, what the ultimate solution is going to be.
Yeah, agreed. We are hitting our time limit now. So I'm just going to do one more question, but the rest of the questions will be answered in our Q&A and networking session here. The third rated one will be, what is the efficiency of generating electricity at a power generating plant using natural gas?
Yeah, I mean, it's relatively low. I don't have the number off the top of my head. It's probably like 30 to 40% or something. And then there's losses in the kind of transmission lines. If you do the calculations, if we're doing natural gas powered generation, what really starts to matter the most is the efficiency of the equipment. Like if we're talking about clean electricity and our goal is carbon savings, so long as you just get off gas, you could even use electric baseboards and you're still having a carbon benefit. And this is the scenario we thought we were in 5 years ago. If we're using a fossil fuel to generate electricity, then generating losses on the grid, then we're fighting a much more uphill battle. Electric baseboards certainly don't make sense, and the lower efficiency equipment starts to make less sense as well. But there's different ways of getting high efficiency. The hybrid approach can achieve a higher efficiency even with a low efficiency unit, because you're only operating it in milder conditions where the efficiency is naturally higher. You could also choose an air source heat pump that was just like kind of premium, top of the line air source heat pump, is also going to be kind of annual COP on the scale of 3.2, if you know what that means. And then, of course, geothermal is really the most efficient option. And in a world where we're generating our electricity from natural gas, like high efficiency heat pumps really becomes the most important thing. And there's a benefit, but the benefit, I think the person who asked the question probably realizes the benefit is much, much smaller than if we had clean electricity. So that's why that clean electricity is really an important part of the puzzle to make this whole approach work.
Great. Well, thank you, Eric, for answering all the questions. We'll have again, Q&A session at the end of our seminar. Please stay until the end. I'll pass this to Aaron.
Thank you. And I just wanted to take this time to thank our speaker, Erik Janssen, once again. Thank you for a very well done seminar and talk. It was very informative, very educational, and it got me thinking about ways that I could reduce my impact on life and the environment. I mean, reduce my impact on the environment as well. So thank you very much for that. I'd like to reiterate, if anyone here is interested, please feel free to follow up with Erik. He has encouraged it, and there are multiple ways you can do that, through his LinkedIn or through his personal contact information that he posted on the slides or in the seminar. And I also would suggest that if you have the chance to follow up with the website he had on his slides as well. I believe it was Sustainable Economy, some around that lines. Erik, if you could just type it in the chat. I forget the exact website.
Sure. Sustainabletechnologies.ca.
Yeah, sustainabletechnology.ca. It was on his slides too, so I would encourage everyone here to go and check that website out as well. But all in all, great seminar, Erik. Thank you so much, and we hope to hear from you again in the future at some point.
Thank you for having me.
Great, thanks very much. So I'm gonna get into just some concluding remarks. Erik had a good suggestion that maybe I give a little bit of kind of personal perspective on my journey to this heat pump. And I'm just going to share my screen here briefly. Share button. Everybody see that okay? So many years ago, I had decided that I wanted to make it my goal to significantly reduce my personal household carbon footprint, but to do so at little to no extra cost. I wasn't sure how feasible that was, but that was my ultimate goal. Being an engineer, I started with calculating my household carbon footprint to see where I needed to make the biggest cuts. And you can see here, before I got into this, my carbon footprint was about 10,000 kilos, 10 tons. Very little of it was from electricity. As Erik mentioned, our grid is currently fairly clean. Close to 3 tons was from home heating, close to 1 ton was from hot water, and 6 tons was actually from the gasoline for our cars. So that's where I made the first cut. I purchased an electric vehicle. We still have a gas car as our second car that we use once in a while when we have to. So, but we were able to cut our carbon down to 700 kilos on that, so 90% cut. And by saving $3,000 a year in gasoline, over 10 years, I'm saving $30,000 plus maintenance. It's cheaper than a gas car in the long term. So I'm actually saving money there. The next biggest cut was the home heating. So I decided to look into that. I considered ground source heat pumps, but those are upwards to $40,000. So that was definitely out of the question. I would never get payback on that. I looked at a cold climate heat pump. As Erik mentioned, they can be fairly costly, $15,000, maybe $20,000, that sort of thing. So that was also out of the question. I looked at an air source heat pump that was low cost, low efficiency, and that's the hybrid system that we talked about. I wasn't sure how much of a cut I would get. My contractor couldn't really give me numbers, but he did point out something that, as Erik had mentioned earlier, in the GTA, we actually have very, very few days in the winter that are below -5 degrees. I didn't quite believe him, so I looked into the Environment Canada website and did some calculations, and he was absolutely right. There was about 20 to 30 days in the heating season that go below that. So I thought, okay, this will probably work. Went ahead and installed it. I needed a new air conditioner anyways. It was 20 years old. It had been undersized since we bought the house. So I was already planning to buy a new air conditioner. And for $1,000 extra, I had a heat pump. So I went ahead with it. And we actually made a big cut. I had done some calculations looking at the data, the COP data from the manufacturer, plus the Environment Canada data. And I'd calculated I'd probably get around 70% reduction, as Erik calculated at the end on the real data afterwards. It was down to about 74%. So it actually did make a big cut. We also cut our hot water usage just through behavioral methods, what Erik mentioned earlier too. So really cut out baths. Nobody's taking baths anymore, very, very rarely. I myself, I'm taking 2-minute Navy showers, that sort of thing. And I was really surprised at how much reduction there was there. We went from 900 to 500 kilos. So again, 45%. All in all, cut of 80% reduction. And in the long run, I'm saving thousands of dollars because of the car. We're spending a little bit extra on utilities each year. But in the long term, as the carbon tax comes in, I'll be saving money, again, as Erik had mentioned earlier. So that's almost a break even, kind of pays for itself for the extra $1,000. End of the day, I've cut my carbon footprint 80% and saved money, not including other things, transportation of goods and, food that we eat and meat and all those sorts of things, flights. I've not trying not to take flights too often, that sort of thing, but just the household carbon footprint has been greatly reduced. So, a big eye opener, something for all of us to definitely consider. In terms of comfort, previously, I again, as an effort before pumps to cut our gas.
It looks like Andreas is cut out. Can you hear me? Can you hear me okay?
Yes.
Can you hear me?
Yeah.
Okay. So I'll just say thank you as well, as Andreas may have gone offline. I'm Jim Chisholm. I'm a regional counselor with the Professional Engineers of Ontario and part of the climate change group that organized this seminar. So I would like to thank the speaker for sure, and also the volunteers, and especially for Andreas for coming up with the idea, with the topic, and being one of the key people to move it forward. This has actually been the 10th seminar that this group, the Climate Change Group, which is a group of PEO members and some people from the wider engineering community, has put on. And the main objective has been to try to put the climate change issue on the radar of the PEO, with the ultimate objective that hopefully the PEO will run with the issue and actually develop an action plan on climate change. the BC regulator has done it. They've shown the way forward, but we have a ways to go here in Ontario, and it's not something that's easy to do. It's a process, and the Climate Change Group will continue to meet to try to drive to that end. And if you're interested in joining us on the Climate Change Group in our journey, there will be a survey through email at the end of this meeting. There will be a question. You can add your name if you'd like to be involved in the activities of the Climate Change Group. And also, we have two engineering speakers groups, the Toronto Engineering Club of Speakers and the Speakers Club of Ryerson Engineering. If you're interested in a speakers club for engineers or people in the engineering community, that is something you could answer in the survey as well. So at this point, I'm going to adjourn the meeting. And as mentioned, there will be a bit of a question networking session. I think Charles is sort of going to be helping us out in that one. So at this point, I adjourn the meeting and call on Charles.
Thank you. Thank you. Most of the questions that arose during the presentation have been answered, but I do have a couple of questions myself coming out of this presentation. I've noticed that there are some land developers who are now developing whole subdivisions with the, incorporating heat pumps and all kinds of environmental improvements, with the advertising of sort of a net zero design. And they're doing everything in insulation, triple glazing of windows, and, many environmental improvements in the home. And I was just wondering if you thought that, if the speaker thought this was going to be a trend.
Yeah, well, yeah, I'm certainly hoping so.
Yeah.
I think that it depends on where the building
Yeah.
code is at and how strongly that can motivate people. But we see, as you say, lots of positive signs.
Yeah.
I saw something come up in my LinkedIn feed recently in Oakville. There was a district heating system, geothermally driven district heating system in a subdivision. If we're talking about new construction, other technologies than just air source heat pumps starts to really make a lot of sense as well. Something like geothermal, if you can do all the drilling kind of pre-construction and share all the heat between all the homes in a district system, that starts to make a ton of sense. So I'd really hope to see more folks moving in that direction. On that realm as well, like looking at the geothermal versus air source heat pumps, I know that the geothermal folks will say, like if we go to that option, then there's lower electricity demand for the subdivision, and that actually reduces the overall development costs as well. So there's lots of really great solutions being explored. Whether or not it becomes mainstream, I guess, depends on regulations and building codes. But it's good to see that. I think we also are getting kind of a more environmentally conscious kind of homeowner base, and the fact that they can advertise it as being constructed to a certain standard, whether that be kind of LEED or whatever else, is a selling point. And there's lots of large home like developers that are helping to move the needle on that. So yeah, I guess that would be my answer.
And I'm also concerned, are we changing building codes? Have you seen some movement, in building codes trying to assess and incorporate? Yeah.
So my focus is mostly on retrofits.
Yes.
Like are interested in retrofits is because like most of the buildings that are going to exist in 20 or 30 years or whatever are the buildings that already exist today. You can kind of, in terms of the regulatory environment, you can kind of demand more of new construction. But it's a bit more challenging to do in existing buildings. I haven't followed up with the code completely. I have heard some criticisms that maybe in some cases not going far enough, but I can't really, unfortunately speak to the details of that, because most of what I do is in the realm of retrofitting or looking at retrofits in existing buildings.
I think that NRC is maintaining Building Code of Canada, in particular in construction. I know I used to work for IREP, and we changed some air exchange from the furnaces, and they changed the piping in and out, which we funded. Maybe perhaps if you approach them for consideration, I think they will be open to the idea. So Building Code of Canada at the National Research Council of Canada. So that's a good idea, maybe to get in touch with them. And I think what you presented here, it's very interesting, and they will be, I think, open to listen. And if you have a good case, I might consider that.
Good.
It's a good suggestion.
I think we've used up most of our allotted time now, so I'm not going to add any further questions. But I, like everyone else here, really enjoyed your presentation, and you did a really thorough job. Thank you.
Excellent. Thanks.
Thank
Thanks
you.
again, everyone, for coming, and thank you to the PEO Climate Change Group for having me.
Eric, can I steal you for 5 minutes? We still have like 4 questions here. If you have time.
Yeah.
Great.
Sure.
There's one question from Ed. He's asking about what is the future of the alternative refrigerants?
Yeah, so I mean, so right now the common one is R410A. It's got low ozone depletion, but still like high global warming potential. I think it's over 2000. I think it's 2088. I just saw this number recently. There's a push to transition towards R22, which still low ozone depletion, kind of lower global warming potential, but it's still kind of, it's several hundred, I think, like 600 or 700 in that range. I think the holy grail is ultimately, we're seeing this with water heating already, is CO2 refrigerant. It's especially well suited to making cold water really hot. And I haven't seen CO2 used in just kind of like a space heating application. You also see in some cases, this is more with gas-driven heat pumps, ammonia being used as a refrigerant, which is also a low global warming potential refrigerant compared to other options. So, I mean, there's work being done there, but I mean, it's important to point that out. We are talking about still using kind of refrigerants with a very high global warming potential, but at least in the context of this talk, we're not really talking about using any more refrigerant than we were already going to if we're talking about hybrid systems, because people already have air conditioners, right? So yeah, the needle needs to move on that as well. We need low global warming potential refrigerants, and I think the industry is transitioning to R22, and then, I mean, I don't hear the talk, but maybe some point in the future to really low options like CO2.
Great, thank you. Next question is, does the HVAC industry know these points? They are still selling lots of natural gas furnace only solution. I believe that's a comment.
Yeah, I mean, it's an awareness gap for everybody in Ontario here. We've kind of, both a blessing and a curse, we've had cheap natural gas for so long that doing something in a different way, like just naturally, there's a whole bunch of ingrained inertia at every level just to keep doing it the same way. And even like you do hear kind of anecdotes of some even like misinformation, like heat pumps don't work in a cold climate and stuff of that nature. I think one of the things we're trying to do in this case is like educate, like show our findings to engineers, to homeowners, to educate them, but also to the contractor and energy advisor community as well. Hopefully they're willing to listen. And I mean, we're ultimately like, everybody's still way, like the same manufacturers of air conditioners, they're also making heat pumps. Like there's nobody, especially in this hybrid system kind of scenario, nobody's losing really. Like everybody's still winning. So it's just a matter of what we're trying to do is fill in the data gaps, show that, hey, this is actually a really good idea. Other jurisdictions are doing it. The local examples we have so far are positive, and just kind of get that information out there to hopefully start to changing the minds of the folks that are on the ground selling this stuff. And there are kind of progressive contractors and associations that they're on the ball. They realize where this is going and are doing this. It's not everybody yet, and hopefully we can end up educating as many of the folks selling and making this equipment as possible to transition towards these greener solutions.
Thank you very much. We have two more questions left. There's one that's asking about, can you explain why refrigerants are so important to mitigating the impacts of climate change and the role of Kigali Accord has in the future of heat pumps?
Okay, this is a very specific question. I'm assuming Kigali Accord has got something to do with like regulations around refrigerant. I'm not familiar with it myself. I know there's a good book out there called Drawdown. I'm sure some of you folks are familiar with it. Like in terms of things we can do it's a book that went through kind of like based on peer-reviewed research, all of the different things we need to do to reduce our impacts, to reduce climate change. I don't know if it was the top of the list or if it was near the top of the list, was reducing our dependency on high global warming potential refrigerants. So it's like, of course, it is a very important topic.
Sorry, Eric, can you mention that guidelines again?
The book was Drawdown, if that's what you're talking about.
Yeah.
Drawdown, yeah. There's some good TED Talks on it and other things like that. The point is that, yeah, high global warming refrigerants is an issue we need to deal with. If you someone corrected me, R32, not R22 to my previous point. Apologies, I misspoke. Yeah, so I mean, it's important to these developments towards low global warming potential refrigerants is very important. But again, to my earlier point as well, we're in the hybrid system context or the air source heat pump system context, we're not talking about using any more refrigerant than we already would have anyway. So it still makes sense compared to kind of business as usual.
Great, thank you. The last question we have here is, for the house built in Victorian era, how much envelope improvement was made through the years to reduce the load and size of heat pumps?
Yeah, so that's a century home. Like that's 100-plus-year-old home. The homeowner did benefit from being a townhouse.
Mhm.
I think being a Victorian home, I forget the number. It's in the case study. There's something like 22 windows in the home, even though it's only got 2 kind of exterior faces. So over the years, she had upgraded kind of many of her windows, but she does still have 9 original single pane ones. At some point, she did a large retrofit to add insulation, I believe, to the kind of building out the walls interior. She's done some draft proofing and things of that nature. But I wouldn't say that it was a incredibly invasive building envelope improvements, because I mean, she's still got many original windows, and those are really the kind of the weak point of the envelope. I would like the point I wanted to make earlier. I mean, sometimes you hear kind of there's different factions here. There's kind of mechanical system people and building envelope people, and each are really excited about their solution. We need them both, and just like air source heat pumps and ground source heat pump, we need them both. There's a lot of synergy to be had. You can lower the building envelope using envelope improvements like air sealing, attic insulation, windows, and that just only makes the building more suitable for a heat pump retrofit. So I would always encourage people, if you're thinking to go the route of the heat pump, it's worthwhile to talk to an energy advisor. I believe that's paid for through the Greener Homes Grant. They can look at your home where the energy improvements in the envelope can be made, and then you can still go forward and do your air source heat pump retrofit.
Perfect. Thank you so much. That will be the last question from the audience, but there's just one popped up asking about access to the presentation today. So after the seminar, we will be getting the presentation from Erik, and we will be posting the video and the presentation on the chapter's website. We will be indicating where you can find all the presentation on our survey as well. So don't worry, this will be available to every one of you who attended to the meeting today. Well, thank you very much, Erik. I enjoyed the presentation today. Thank you so much.
Nice meeting you all. Have a good one.
Ready?
Is Andrews here?
Yeah, I'm still here. Have you stopped the recording?
Yes.